In the previous video, we looked at two sequences, A and B, and used our intuition to generate two possible alignments. Now, of course, a computer doesn't have such intuition. Therefore, we need to provide a step-by-step instructions of how to perform this task. In this video, we will be following each of these steps so that we understand the algorithm. Now, as mentioned previously, Gotoh's algorithm is a dynamic programming approach. Therefore, this video series assumes some familiarity with dynamic programming and memoization. Just like all dynamic programming, instead of looking at the problem as a whole, we break it down into smaller subproblems. In our case, smaller subproblems are shorter sequences that increase in length by 1 for every iteration. So, we start looking at the sequence from the first element, and then we increase the number of nucleotides at every iteration. And same goes for both sequences. Now, there are three things that can happen at every iteration. And we will be going through each of these three cases. But first, assume that we already aligned some portion of the sequence before this red line. And we are looking at ith and jth nucleotides in A and B sequences. So, the first thing that can happen is that sequence B can end with a gap, while there is a nucleotide in sequence A. The second thing that can happen is that A ends with a gap, and we have a nucleotide in B. Lastly, it can happen that neither of the sequences end with a gap, so we have two nucleotides aligned at ith and jth position. Now, this instance can further be broken down into two cases. First, when the last elements are the same. Second, when last elements are not the same. This is the case of substitution, where we have nucleotides that are different. So, for example, we can have A and T. In case of a substitution, we want to penalize the alignment, and we do so by giving it a penalty of 1. However, when the two nucleotides are the same, in this case, we like the alignment. There's no event that's happening, so we don't penalize. So here, the penalty score will be 0. We track each of these three events using three memoization matrices. The first instance, where the sequence B ends with a gap, is tracked by memoization matrix P. The second instance, where A ends with a gap, is tracked by memoization matrix Q. Lastly, we have a memoization matrix D, which tracks the optimal decision at every point, and this includes the previous two events or the event of no gap at all. Finally, we are ready to start filling out the memoization matrices. On the left panel, I provided a few pieces of information that we need to keep in mind throughout the process. The first piece of information is that we have two sequences, A and B, and we need to remember what these sequences were. Second, we have defined the gap penalty cost, specifically U, which was the cost of extending a gap, to be equal to 2, and V of cost of inserting a gap to be equal to 5. Lastly, we need to remember that the matrix P corresponds to ending the sequence B with a gap, whereas matrix Q corresponds to ending a sequence A with a gap. Over here, I provided a tracker for our I and J values. As you can see, the I value can become 1 or 2, and this corresponds to the maximum length of 2 of sequence A. J can have the value of 1 to 4 included, and this is because B has a length of 4. On the rightmost panel, we have the recurrence relations for each of the three matrices. For P, in order for sequence B to end with a gap, there are two things that may happen. First, if there was no gap before, we may have to insert a gap, and this is what the first part corresponds. Note how we have V over here. This is because we are inserting a gap, therefore we have to penalize the alignment. Alternatively, if there was already a gap, then all we need to do is extend the gap. And this is why we only have U. The Q is the same two options, but for A. So over here we are inserting a gap in A, and here we are extending a gap in A. Lastly, we have matrix D, which tracks the most optimal decision at every point of recurrence. So we have three options. First, ending the sequence B with a gap. So ending the sequence B with a gap. We have second option, ending sequence A with a gap. And lastly, not having a gap at all. In this case, remember how we could have two options. First, the two nucleotides could match, in which case we would not penalize the alignment, or there could be a mismatch between the nucleotides, also known as a substitution, in which case we would penalize the alignment by 1. Now it is time to initialize the matrices, and we will start from matrix D. Here, in order to fill out the edges of matrix, we can use a affine gap penalty equation that we discussed in the first video, which was GK is equal to U times K plus V. So for instance, if we take this submatrix where we have two empty sequences, then there's nothing to align and there is no gap to apply. Therefore, we'll put a 0 in this cell. Next, we can look at this cell where for sequence A we have the nucleotide A, and for sequence B we have an empty set. In this case, we have the following situation where sequence B consists of one gap of a length of 1. Therefore, we can calculate a gap penalty as follows. G of 1 is equal to 2 times 1 plus 5. So 7. For C, for this cell, we have AC and an empty set. In other words, AC with a single gap in B of a length of 2. Therefore, we have G2 is equal to 2 times 2 plus 5. 9. Note how as we add the nucleotides in the first column, the gap penalty increases by 2. The same applies in the first row. So we would start with 7, 9, 11, and 13. This is because every time we add a new nucleotide, we extend a gap by 1 nucleotide, which costs 2. The next step is to initialize matrix P. And we'll do this by putting infinity in the first row. The reason is we don't want to start sequence B with a gap here. And this is because in the first row we are looking at sequence A of empty set and sequence B of A, C, C, T, depending on where we are in the first row. Now there is no reason for us to align an empty set with a gap, which is, remember, what P was doing. So it was inserting gaps in sequence B, and there is no reason to do that if we have an empty set in the first sequence. Therefore, we put infinity so that this decision is never the minimum. We do the same in Q, but instead of a row, we do it in the column. This way, we make sure that in no instance does sequence alignment A start with a gap, so we don't have an empty set aligned to a gap. Now, we won't be referencing to the first column of matrix P and first row of matrix Q. Therefore, we can keep it as 0. The rest of the algorithm is essentially following these recurrence relations until we fill out each of these matrices. I will provide an example of the first cell over here. So this is I equal to 1 and j equals to 1, so we are standing right here. And I will also provide the example of the last cell. So let's get started with matrix P. Matrix P, the first line is referring to the matrix D. So now we want to look at D at a cell of I minus 1 and j. And this is over here. Because I minus 1, it would take us one row above. So we have 7 at this location, and we want to add u and v, which is 2 and 5, therefore 14. Now, for the second line, we are also referring to the cell above, so over here, but in matrix P, and we have infinity plus 2, which is infinity. Note that we want to find the minimum of these two, and this is because we are trying to minimize the distance between the two sequences. So, of course, 14 is less than infinity, therefore we will put 14 in this cell. Now let's move to matrix Q. Again, this is referring to the matrix D, but instead of taking it a row above, it's taking a column next to it because we have I and j minus 1, which is a cell over here. Again, this is equal to 7, and we want to add the cost of extending a gap and cost of inserting a gap, which is 14. And here it should be Q actually. Apologies. So for Q, we want to look at the same cell, one column left, which is infinity, therefore infinity plus 2 is equal to infinity, and again 14 is the minimum value, which is what we are going to put in the matrix. Lastly, we need to fill out matrix D. Matrix D wants us to look at P at I and j, so the values that we just filled out, which was 14 in both cases, and we also want to look at a cell I minus 1 and j minus 1, which is a cell that I just pointed at. So we have 0 plus, and then we have this delta equation, which checks whether there's a match or a mismatch. And because it's an empty set, there's no match or a mismatch. Therefore, we're going to keep it 0. Therefore, we need to take a minimum between 0, 14, and 14. And of course, we will keep 0. Now, I will fill out the rest of the matrix until the last cell, and we will repeat these calculations for the last cell. I filled out the rest of the cells except for the last cell of each of the matrix. So right now we are at I equals to 2 and j equals to 4. And we are going to do the same thing that we did for the first cell. So again, we are starting with matrix P, which in the first line, it's referencing to the matrix D. And it wants us to look at this cell at the position of I minus 1 and j, which is right here. So this would be 11 plus 2 plus 5, which is equal to 18. In the second line, we are looking at matrix P in the same location of I minus 1 and j. So over here, which is 20 plus 2, which is 22. So of course the minimum is 18, which is what we are going to keep. Let's move to the matrix Q. Here we are looking at the cell that is one column to the left. So the position of I and j minus 1, which here it's equal to 7. So we'll have 7 plus 2 plus 5, and this is equal to 14. And again, this should be q. Okay. And then we're going back to the matrix Q in line second, and we are looking at the cell in the same position of I and j minus 1, and this is also 7 plus 2, and it would be 9. So here the minimum is 9, therefore we are going to keep 9. Lastly, we have matrix D, which takes the minimum of the past two calculations. Here it was 18 and 9, and also it's looking at the cell over here. So at cell of I minus 1 and j minus 1, we are looking at nucleotides A and C, and as you can see, this is a mismatch. The two nucleotides are different, therefore we are going to penalize the algorithm by 1, and it's going to be 9 plus 1, which is equal to 10. Now we have the options of 10, 11, 10, 18, and 9, and of course the minimum is 9, and we will keep 9 over here. We finalized our matrix, and the next question is, of course, what do we do about this? How do we translate this into an alignment, which is the topic for the next video.